and how it's going to relate to horizontal asymptotes from back in the day. So we're going to do a course infinity, and then we'll get into the sequences at the end. Alex, focus, please. In this section, we study a special kind of limit called limit at infinity. Of course, we're taking a look at when x is becoming larger and larger and larger and larger. Now, as always, I can't do direct substitution with infinity. That's why I said have your graphing calculators out. We might look at some graphs today to help us. We might have to look at some number patterns, etc., that sort of thing like that. So, of course, you've got that table there in front of you for the function. Notice they have the plus or minus on here just to show you positive, negative numbers. As x is getting bigger, obviously, if I pulled up the table, it's very clearly to see the limit is approaching 1. Looks like a 1 to me, okay? Also, if you look at the graph over here, Alex,
I'm helping Ryan.
Can you focus, please?
I'm trying to look at, sorry.
If you look at the graph, and of course mine is in blue of our actual function we're talking about, it is approaching 1. That horizontal red, mine's red, yours isn't red, that horizontal red line, that asymptote, horizontal asymptote, there's a throwback to chapter 3, is going to come into play, and I'm going to show you how you can kind of use those to help you with your limits today. So, in fact, of course, as we're getting these larger and larger numbers, as you can see, infinity, obviously we're going to say the limit approaches 1. So we can look at the table. We can look at the graph. I could not do direct substitution. How are we going to plug infinity in there? Okay, so of course, this is nothing exciting. As of course, we're approaching infinity. If you can come to a value like 1, that of course is our limit. Now, that is also going to be coming at us our horizontal asymptote too. That's kind of the relationship between all of this good stuff. So for numerically large negative values, it's the same thing for negative. Clearly you're going to the left. So if you look at this function, mine's blue, of course, is I'm going to the left, keep going to the left, everything going is in a box to the left. You are getting close to that red line at 1 also. So it doesn't matter, it just depends on which side you're looking at. Positive infinity to the right, negative infinity to the left. And again, you can see that from a table. It's approaching 1. We can see it clearly from the graph. I cannot do direct substitution with negative infinity. Doesn't work out. All right, same thing here. We're just saying, of course, if they approach a value that, remember, is also our horizontal asymptote. So I know I keep talking about these horizontal asymptotes, which is a throwback to chapter 3, because once we get the relationship down that it's really approaching a horizontal asymptote, our math, our work today is going to be super easy for you. But we can't start out super easy. We have to get through the y first. And again, you can see your horizontal asymptote there. Okay, so for this one, of course, we're approaching infinity, negative infinity. Couple different ways you can look at it. I'm going to do, of course, the infinity one first. Now, if you have kind of a number sense to you, some of you might be able to look at that and say, well, I can tell you what it is right now. I'm thinking about if I keep putting larger and larger and larger and larger and larger and larger numbers in here for x. You're going to get close to 0 because 1 divided by a very large number pushes you closer and closer to 0. Now, of course, you can also look in the t-chart on your graphing calculator. But again, I didn't really do a lot of crazy math. I didn't even throw out the graph. I didn't even bring up the table. I just used some number sense. The larger this is getting, the closer to 0. What if you go negative infinity? So if you're putting in larger and larger and larger negative numbers, 0. Now, again, I keep talking about these horizontal asymptotes because I'm going to try to make your life easy. I just happen to know what the graph 1 over x looks like. That's a very common function. So I'm just going to sketch a quick graph. You could punch it in your calculator, of course. I'm just graphing 1 over x. Again, rough sketch. We know my drawing skills. It looks something like that. So of course, if you wanted to look at the graph, as we're approaching, of course, negative infinity, we're going out to the left, you're getting closer and closer to this asymptote of 0. Same thing here, positive infinity, it keeps curving down, you're going to get closer and closer to your horizontal asymptote of y equals 0. So your horizontal asymptote is really kind of your winner answer today too, when we start looking at some of these graphs and sequences, etc. All right, that's as wild as that's got to get. Now, let's talk some limit laws, because I know we love our limit laws. So, at least we don't have to justify anything. They feel happy about that. So, limit laws, of course, we just studied back in 13.2 are true at infinity. Now, especially there was that power one in that special case. So, k, of course, is your exponent. So, think about this. As x is getting bigger and you're raising it to a power, I mean, that's going to get to a huge number as you're getting closer and closer to infinity. We just kind of saw in our easy 1 over x, that one went to 0. Clearly, if you slap a power on x, it's going to go to 0 too. You're going to keep having a larger and larger number in your denominator. So, here's the yuck part. We got to do the work first, so I'm going to make it easy for you. Got to start hard, then go easy. So what I want to do, of course, is use our limit laws. Find the limit as x approaches infinity. So I'm going to write it out nice and pretty. Approaches infinity. Okay, so I cannot use direct substitution. I can't put infinity in, that just seems weird. So here's kind of the play you have to make. Because I'm going to click it back a slide here. I want to use these limit laws and these exponent properties. So I'd like to have some it doesn't necessarily have to be 1, but like 1 over x squared. 1 over x, that sort of stuff, because I can tell you those limits are 0. So what I'm going to do, because it's the denominator we really care about, I'm going to take a look at this, I'll circle it in green, this x squared. Now I can do whatever I want to a fraction as long as I do it obviously to everything. So I see I've got that x squared in the bottom, all 4 terms, negative 2x3, 3x squared 1. I'm going to divide those all by x squared, and you'll see why in a minute. Okay, I'm going to start with bottom, the easy ones. Divide by x squared. 3. Divide this by x squared. Got it. Now, 3, I'm going to do the 3. That's easy. Okay, negative 2x. Now, we're going to divide it by x squared, but of course you can reduce those x and x squared down to just a single x on the bottom here. So really I'm just going to cross this guy out, try to on the smartboard, and cross off that. Now the reason we did that is those power rules on the previous page. If we put a larger and larger number in here for x, I can tell you the limit of that expression. Same with this, same with this, same with this. If you remember back to 13.2, which we're not going to write it all out and justify all our steps, you can use all those limit properties where you can apply the limit to each expression in here. The limit of the numerator, the limit of the denominator, limit of a quotient, limit of a sum, limit of a sum. You can basically slap the limit on all 4 of those with all those limit laws. Now, do we have to write that all out this time? No, we've been through that. We're just going to do the limit of each fraction. So if I think of this, bigger and bigger x's, this is going to get close to what number? 0. If I put bigger and bigger x's in here, this is going to get close to 0. This thing's almost worthless, okay? 3 is 3. And same deal. If I put bigger and bigger numbers in here, this will approach 0. So we did all of that work for a lousy answer of 0. Okay, let's try this. Now, similar function. I didn't have a mental breakdown. They are super close. You're going to see why. There's a pattern. Clearly, they're close. I just, mixing it up on you. So, same thing, approaching infinity. I can't use direct substitution. Okay, same spiel as the last one. It's really that denominator we're concerned about. So I'm looking at the bottom. I'm going to do the same thing. I'm going to go through and divide everything by x squared because I know any value over x to a power is going to approach 0. Okay, so I'm going to do the same thing I did over here, basically. I just mixed it up on you a little bit. Okay, so again, if I divide, I'm going to start on the bottom. If I divide this by x squared, I just have my 3, my 1 over x squared again, my 3 over x squared again. It's really this one. When you divide this by x squared, we just have negative 2. Now, according to our limit properties, our limit laws, which we're not going to get crazy, write everything out, we can do the limit of the top. Might help if I remember the plus. Limit of the top, the limit of the bottom, limit of the sum. We can do the limit of all of those separately. I'm not going to write out the word limit 4 times. We're just going to do it. So, of course, negative 2 is negative 2. If I put larger and larger numbers in here, the limit of this expression would approach what? 0. 3 is 3. If I put larger and larger numbers in this expression, it's going to approach what? 0. So similar, but we get a nicer answer, a little nicer answer. Okay? Last one, and you'll hopefully see a pattern. Hopefully. Okay, notice I put it up to cube now. Same deal, same deal. I'm going to write out limit. Okay. Now, same thing. I'm doing the exact same thing as on all the others. I'm looking at that denominator. I'm going to divide everything by x squared. So I can use that limit law with the powers. We know it. Okay. All right, I'm going to start on the bottom again. I divide by x squared. I know we're shocked it's 3. 1 over x squared. 3 over x squared. Okay, and when I divide this by x squared, you're going to have what? Negative 2x, which seems right. Okay. So again, I feel like I got to give the same spiel. We can use our limit law, limit of a quotient, limit at the top, limit at the bottom. Then I can use my limit laws of a sum, where I put the limit on every term, which we're not going to write all of that out because it's obnoxious. We're just going to take a look at the limit of each expression. I'm going to start on the bottom. I'm going to start easy. 3 is 3. Larger and larger numbers in here. Again, that will get close to 0. Same thing, 3 over x squared. Larger and larger numbers in for x. That's going to approach 0. And this just looks weird. So, question for you. Are you going to get a distinct numerical value for an answer? No. So, DNE. Now, before, I'm going to click it back a slide. Before I wrote out anything, because I know how these relate to horizontal asymptotes, I could have told you the answers on these with 0 amount of work.
Oh, why didn't you tell me that?
And just because I love you, hey, this is straight out of 3.6. There's a flashback.
What?
Remember when we did all those horizontal asymptotes? The rules are the same here, my friends. That's why I pulled out my 3.6. Okay. Look at the degree, the highest exponent of the numerator versus the denominator. If the degree of the numerator is smaller than the denominator, it is automatically 0. So I knew this was going to be 0 with no work. Because I have x to the first, x squared. Whenever the top is smaller, my horizontal asymptote 0. I did 0 work. I knew it was 0. Done. I also knew when our ratio of the degrees, they are the same, squared and squared. So letter B, squared and squared. It is the ratio of the lead coefficients, we call that. Lead coefficients.
Do we have to show any work done?
So, just wait. So I saw those squareds and I knew it was negative 2/3 with no work. Then, of course, when you look at C, I'm going to click it ahead there, where the degree of the top is bigger. Well, I knew from all of our asymptote work, bam. When the degree of the top is larger, that kicked us into that slant asymptote, which remember we had to use long division to find it. That was really a whole bunch of fun on that one. So I knew that C was going to be a does not exist. So let's kind of summarize this because it's been a while. So what do you notice about the answers in the relationship to the horizontal asymptotes? Well, they're the same. Now, you might, because, chapter 3 was, I can't even tell you what month, we might need to add a little summary of this. So, if the degree, now remember, degree is the highest exponent. If you need a note on that, hopefully you know that. If the degree of the numerator is smaller than the denominator, of course, it was automatically 0. So I knew that A was 0, I didn't do any work. If the degree of the top and bottom are the same, so I'm going to put degree of numerator equals degree of denominator. And I'm just abbreviating, obviously you can do.
There it is.
Then it's the ratio, I should put y equals on that, of lead coefficients. So that's why I knew right away B was negative 2/3 with no work. Now, obviously, C is a situation when the degree of the top is larger. That kicks you into a slant asymptote, not a horizontal asymptote. So that's why I knew C is a DNE. It does not exist. If you need to put a note on that, why this is a DNE, because the degree of the top's larger, because you have that cubed versus a squared, make yourself a note. But hopefully, now that we've talked about that from chapter 3, it's a little fresh in your mind. The only thing I'm going to say about like this green one, when the degrees are the same, let me click it back to B. Not that this happens a whole lot, but just be aware of it. Sometimes they might have these terms in the incorrect order in my eyes. Like maybe the bottom they have a 1 plus 3x squared. Just realize we need those highest exponents down to the lowest, because that's obviously super important when I'm looking at the lead coefficient. They might have the order scrambled. You may need to unscramble it. Not that that's the end of the world. Okay, moving right on. So let's do our sequences. Sequences, of course, good tie into the last chapter. Limits of sequences have many of the same properties as the functions. So, here, nice, easy sequence, good review, final exam coming up, super easy, write out the first 5 terms. You know, I'm not even going to write A1, A2, let's just get the fractions. Always start with 1 unless they tell you something else. So if I put 1 in here, 2 to the first is 2. Let's put 2 in, 2 squared, 3 squared, or 2 cubed, I'm sorry, what's 2 cubed? 8. I don't know, how many more? Let's do one more, I guess. What's 2 to the 4th?
10.
Okay.
Our code.
I mean, I could keep on going, right? Well,
Fifth all.
can you tell the limit right now as you approach infinity? 0. Because we're going to keep getting larger and larger denominators. Those are going to get closer and closer to 0, just for the record. So that's what this is talking about. So the terms of the sequence get closer and closer to 0. Little vocabulary for you. We say that it's convergent or converges to 0.
Divergent.
And then divergent means, of course, it doesn't come to a number. It's a DNE. A DNE. Okay. So that's what this is saying to you. So you can, of course, converges or be convergent. Otherwise, DNE, we say it doesn't happen. So instead of saying DNE on these sequences, it's just a shift in the vocabulary. Now they're going to get fancy and say it's divergent.
Is that a
Okay.
movie?
Yes.
Is that a movie?
Yes.
Interesting.
Leonardo DiCaprio?
Interesting. Okay. Find the limit of each sequence. Assume it begins with 1. Now, you've got some choices here, my friends. I'm going to show you one thing on your calculator. So we could look at the table, of course. So I'm going to y equals here. Of course, I'm going to use x. I'm not going to switch to n. I'm going to do the alpha y equals to pull up that horizontal fraction bar. And I already forgot. What is it? 2n plus 1n plus 4. 2x plus 1. Yeah, x plus 4. Now, here's the nice thing. This is why I'm showing you this too. If you use the alpha y equals in the y equals menu, it will kick your fractions out into your table. It won't give you the decimals if you like that, especially, full of pro tips this week, if you're on the final exam, which is multiple choice, and I'm not looking at your work, and I ask you for the first 5 terms of the sequence. Get them off your table. Why am I going to mental math anything? Let's get real about it. Okay, so we're looking for the limit as we approach infinity. I mean, I'm only at 8, for goodness sakes.
Wait, why didn't mine do fractions? 1.
That's why I said that's.
I think we're bigger than 1.
No. Wait, you did y equals, right?
Yes.
Alpha y equals?
Yes. I mean, 7/4 is 1 3/4.
That is true. Wait, how does I?
2.
So right now, I mean, I'd have to keep scrolling a ways to really get a good gut instinct, but I am kind of thinking too, right?
Yep.
I am. Okay. Now.
Answer 2.
Now, oh my God, he's coming up here. Same thing. So the limit, we're going, and I should use n, not x, sorry. N. Because remember, your sequences go on forever. I mean, I could write out the terms forever. So this is why we're approaching infinity. Now, is our expression for this sequence a rational function? Rational function, is it a fraction?
C.
Yes. So we know from my big spiel that it's the same as the horizontal asymptote. What is the horizontal asymptote here?
Oh my
Two.
God, I was right.
So I don't care how you get the 2, whether you look at the table and you're looking at the fractions and you see you're getting close to 2, or you look at that and it's like a rational function, I'm going to use the horizontal asymptote.
Oh,
This
okay.
time, I'm just going straight rational function, okay? I'm not going to look at the table. I'm not going to write out any terms. We're just going to do it. I keep wanting to write x instead of n. Okay. Because remember, while we're approaching infinity, your sequences go on forever. Dot, 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 dot. Now, rational expression, exponents, degrees are the same. I know it approaches the horizontal asymptote, which what would be our horizontal asymptote here?
1.
1. Lead coefficients, ratio of the lead coefficients, 1 over 1. Again, you could look at the table and scan through it and see that it gets close to 1. Let's go back to full screen. I don't think I need my calculator anymore. All right, let's do this guy. Now, same thing. We're approaching infinity. It's a sequence. They technically go on forever. I like that it is a rational function.
Oh, shoot.
So again, I know it approaches the horizontal asymptote. Our horizontal asymptote on this case is what? 1/2. 2 over 4, 1/2. The lead coefficients. Got it. So I think I don't want to. I think it was it Alex that asked, like, do you need to show work on these? What am I gonna say?
No.
I just care that you can get me the 1/2, that you know how to get the correct answer. Whether you're looking at the table, whether you're using your horizontal asymptote knowledge, as long as you can get it. All right, determine whether the sequence, okay, now here we go, people. I cannot use my rational function horizontal asymptote spiel because it's not a rational function. It is not a fraction. So I'm going to go old school. I'm either going to punch it in my calculator and look at the table. That's not that bad of a function. So I think I'm just going to mental math it and write out a handful of the terms and see if we see anything. So if I put 1 in there, what's -1 squared?
1.
-1 cubed. -1 to the 4th. Well, we could do this all day, right?
It's
So-
divergent.
So is this going to approach a limit?
No.
No, because it's alternating between 1 and -1. We've got a jump. Remember we talked about the jumps earlier? So this is divergent. So instead of saying, and this is just a nitpicky -1/2 a point thing, if you wrote D and E on your test here,
You get point out, half a point out.
because it's
1/3 point off.
But you got the D.
1/3 a point.
It-
I
the
had a
working
kid from
version has
college.
D and E in it.
I had a kid from college email me this year that their professor in college, because the kids always get mad at me on my half-point deductions, that their college professor took quarter points off. I was like, oh my gosh, who can grade down to the quarter point? I can't do that.
Sorry, divergent has D and E in it.
It's not that much to remember, people. On a sequence, we use divergent. We can handle that. All right, find the limit. Are we ready? Man, we're on the last one. I'm kind of scared. Now, that is to me a hot giant mess over there of stuff. So I'm going to try to simplify it a little bit. I don't even personally want to type that in my y equals menu. I just feel like it would be very tedious. Okay, so again, you're going to see this in tomorrow's section. This is kind of a familiar expression. This to me seems weird. We're multiplying. I'm just going to put the 8n, my n plus 1, my 2n plus 1. This bothers me in the bottom. I like the number first. Okay. Now, here's the thing. I think we can figure this one out with very little work. At least it looks bad, but I think we can do it without a lot of work. Because, is it a rational function? Yes. So if I can figure out the degrees, I can use my horizontal asymptote knowledge. So I'm like, okay. If I FOIL this junk on the top, and I might FOIL it all out. Let's just talk about if I FOIL it. If I FOIL it, what would be the degree on the top? 3. They'd be cubed. I'd have a cubed and a cubed. So I need the lead coefficients.
16 over 6.
Can you figure out what the lead coefficients are right now?
16 over 6.
If we FOILed it, we'd have a 16 and a 6, right? Can you reduce it?
Brother, you
8
don't.
over 3.
Got it.
And we're done.
And we're done.
Bang.
So, I mean, you could FOIL it out and simplify it and look at it, but as long as you can see, hey, I just need that lead coefficient, it was E16. Yeah, see, that wasn't that bad, was it?
No, it was.
I'd be owning